Hey everybody, welcome to the determination of the Ka for a weak acid. What you see here is just kind of a guide for you. You can see you're increasing how your base strength increases, how your acid strength increases, whether you're going up or across that periodic table. So let's just go ahead and get right into it. I think the first thing that we want to note is we're going to be given the chemical equation of any generic, well actually this is the chemical equation for any generic monoprotic weak acid, or what we're going to call our HA. So when you say, we're going to call that our weak acid. It's an equilibrium expression. It can be written such that the concentration of the products divided by the concentration of the reactants is equal to some constants, which is labeled Ka for acids. Okay. So since both hydronium ion concentration and acid equilibrium constants are frequently very small numbers, remember I said they're very small numbers, these numbers are often expressed as the negative logarithms of the original number. Now, these new numbers are indicated with a P for power of 10, so that the negative hydronium ion concentration is abbreviated as P. Okay, so similarly, the negative log 10 of the acid equilibrium constant Ka is abbreviated with a P and Ka, so pKa. You can take the calculation the other direction as well, and that's what you're going to see on this third line here. So make sure you're using the correct number of sig figs. Don't forget sig figs during this lab. All right, now since the simplified numerical values of logarithmic expressions can be easier to work with, we're going to take the negative logarithm, which you're going to see here, and do some rearranging. And we can get this equation, which is known as the Henderson-Hakelbach equation. The Henderson-Hakelbach equation. Well, there we go. Now, I apologize. Let's go right back here. Now, in this experiment, we're going to use the Henderson-Hakelbach equation and the fact that the log, or 10 times 1, equals 0. So that right here, we'll simply simplify to pH is equal to pKa when A negative equals HA. Okay? Exercise to design an experiment so that the point where your A negative is equal to HA is known. Now, I'm jumping right back over where we just were. I apologize for jumping ahead. Starting with an concentration of any weak monoprotic acid, which is your HA, again, we can figure out a known volume of the acid. A titration of this acid with a strong base to the equivalence point will convert all the HA to its corresponding salt and water. After reaching the equivalence point, you have no more HA left. It has all reacted with NaOH for the A negative, water, and the spectator cation. If you backtrack to halfway to the equivalence point, you should recognize that this is the point where half of the HA has been converted. At this point, the pH is 10 pKa to calculate the Ka of the acid. Excuse me. Now, we're just going to kind of go through these. I'm going to kind of skip through the questions, but I just want to make a note here to determine the approximate equivalence points for the reactions of acetic acid and the unknown acid with NaOH. Okay, we're just going to keep that in the back of our head. We do have some. I don't typically ask these bonus questions, but I will ask them in the video. You can write them on paper and bring them to your next meeting, which is going to be for this lab. I will not accept it late, but here are some questions. Let's see. What are you determining in the titrations you're doing? That's number 1. Okay. Now, number 2, how many titrations will be precise? Number 3, what happens to the pH at the equivalence point? Number 4, how should the NaOH solution drip into the beaker? And number 5, where will you see your jump in the pH reading? All right, so for the determination of the Ka for a weak acid, if you have questions, make sure you're reaching out. I'm happy to help any way that I can, and good luck in the weak acid lab.